Thank you. So for the one who are not, was not enough of 8 lectures of during this last semester, we have another part about what we're doing in the lab. So here what we're going to talk and present today is basically coming back to exactly what Lydéric said this morning, is how we can develop things to see in a certain way what is happening at a small scale. So of course what we have seen in this morning was basically using ions as a probe to observe what is the dynamics of the interface. And in parallel to this, we also were interested over the last 10 years now to develop alternative techniques to investigate what is happening for fluids in general and even more, let's say, condensed matter material when you confine them at the nanoscale. So what we did was, the idea is basically to borrow what has been done in surface science since 80s, so 40 years, and basically take a scanning probe microscopes, or different kind of scanning probe microscope. By microscope, in our case, mostly atomic force microscope, and use it for liquids. So we're going to see 3 different, so basically in a sort of a historical overview what we have done, starting with the first experiment that have been done here in Paris on confined liquids. Then we were going to see just how far you can push these techniques, and then we just try to demonstrate that you can use this technique also to investigate what is the physics of interfacial water, let's say. Even though we will not talk about water in this talk, we're going to see any kind of liquids, even sort of solid liquids that we see. So we're not talking of water, but other kind of fluids. So the first thing that we were interested was a certain way to use an AFM in the most canonical configurations. Was the idea to use atomic force microscopy to confine fluids between a probe and the surface. And Benjamin presented quite briefly what we have done at the beginning. Was what we are interested was basically to study the mechanical properties of ionic liquids when they are confined between metallic surfaces. The interest of ionic liquids is that it's a model system for SPM experiments, because it's a molten salt that is only based on charges and basically ions, let's say. That is a liquid at a room temperature. It doesn't evaporate, so it's very stable, and this helps a lot for experiments. So, if from one side, from an experimental point of view, it's a quite a good material, from a fundamental point of view, it is quite interesting, because exactly, since it's only charges, the physics that governs this liquid is basically electrostatics. And a part of that is, of course, a liquid that has been, that is used a lot also in application, for example, in energy storage, as an electrolyte for supercapacitor, but also more like produce mechanical properties as lubricants. So, we will not describe too much about which kind of ionic liquid we were using, but basically it's this sort of unpronounceable name here is that we're going to call it BMIN BF4. That is basically, as you can see, quite a big molecules in the order of 1 nanometer, so it's much bigger than the case of a water molecule. And it is basically based on these 2 parts. One is the positive ions, and the other was, let's say, sort of a negative, and the 2 are not symmetric. But apart from that, we just consider that it's just a series of charges. And what we wanted to do is that basically, I was just saying, make a study with the tuning fork-based atomic force microscope. So experimentally, what was interesting and what we did was, is it true, and what is the interest of using atomic force microscopes, and what is the kind of experimental configuration that we decided to use? So we wanted to use basically this an AFM to confine the liquid between the tip and the probe. And we wanted to use a sort of a macroscopic liquid. We were looking for a configuration where it was possible to use and handle macroscopic surfaces. So using a real or say commercial atomic force microscope was not exactly the ideal case for several reasons. First, because it's not very versatile, but also because to have high resolution, the level that you use in an atomic force microscope is in general very, very soft. That it translated in big instability. And this is not great when you work with the liquids and the interface. So we decided to really use what has been developed in surface science to reach ultimate resolution. So basically use atomic force microscope based on a macroscopic oscillator that are, in this case, a quartz tuning fork, that are characterized by a very, very large stiffness in the order of tens of kilonewton per meter, and this as a consequence of guarantee a big stability. So you can approach the surface without between experiencing any jump to contact. So it's very good to investigate what is happening when you confine the very small scale. And together with this high stiffness, it also comes with a high quality factor. So it means high sensitivity to measuring force. So the idea is, as you can see here, you take the ionic liquid, you put it between a metallic probe, that in our case was a tungsten tip, and a metallic surface. And what you measure is basically the mechanical response of the tuning force. You do not measure directly the mechanical response of the liquid, but you measure how the oscillator responds. And in our case, it's a resonance measurement, so we investigate what is happening at its resonance, and we can separate the two components. That is one, the conservative force, that is basically the shift in the frequency, in the frequency resonance frequency, and also the sort of the dissipation or the damping force that is translated by this change in the oscillation amplitude or increase of the width of the resonance. And I enter a bit more into the details because basically this is what we do for all kinds of experiments. So this is the common aspect of everything that we're going to see today, basically for every kind of a device. So the idea is always we use an oscillator that we as a probe sensor, as a force sensor, and we investigate how the response is changed by the interaction with the environment. And most exactly by studying this, we're measuring the conservative part and the dissipative part. We can have access directly to the rheology, let's say, or to the impedance of the mechanical impedance of the surface of the sample of the sample that we are investigating. So that was the experiment. So what we go show here was very simple. The idea was, in principle, was simple. Is that okay? We start to confine. So what is happening when you approach the probe, the tip to the sample? So when you're quite far, you basically recover a very, very simple viscous behavior with a dissipation that is increasing following the Reynolds force. And this goes quite well up for confinement down to a few hundreds of nanometers. And the stiffness stays almost zero. At that time, we considered this is zero. Right now, we start to discover that this small negative stiffness is not an artifact or is not strange. We do not know what is exactly the origin, but we start to understand that there is somewhat more information that can be obtained from this, but for the moment we have no idea. But at that time, especially, we were saying, okay, this is very, very small, so it's basically probably either an artifact or some parasitic force. We are not interested. And then, okay, we kept confining. At a certain point, when we were at 50 nanometers, a distance that we were obtained by basically extrapolating the hydrodynamic zero, we observed this slight big change in the mechanical response with a sudden change in rupture in the dissipative part, but most importantly, with the change in the conservative part. And this slight change was at least for us, was considered like a signature of a phase transition between a standard liquid behavior to something like more solid, characterized by basically a stiffness or a rigidity. So we did this experiment for different samples, for different surfaces. Here, for example, we used an HOPG that was nice in terms of, this is very flat. And then we did it more like trying to understand what is happening when you change the surface. So we started with the HOPG, but then the first idea was to investigate if the mechanical, so if the electronic properties of this of the surface could have an impact on this confinement, let's say, critical confinement distance. So we performed this experiment with mica. We observed that basically this critical confinement length was in the order of a few nanometers. That was in agreement, more or less, compatible with sort of terraces that are static terraces that are formed on the surface. And then what you observe is that when you increase the metallicity, you observe this strong increase of this critical confinement. And here what we plotted was this freezing length as a function of the inverse of the Thomas Fermi wavelength. And so you observe that more is the substrate is metallic, more the conductivity is higher, larger, and more you have this, you facilitate this transition. And at that time, and it's also what Benjamin presented and described very well, we ascribed this with the sort of electrostatic interaction between the molecules in the ionic liquid and the electrons in the sample. And somehow we were able to recover this behavior by considering a perfect screening compared to non-perfect screening. And this for us was sort of the first time we were able to observe a real relationship between the properties of a liquid and the properties of the electronic properties of a substrate. Unfortunately, in this sense, or let's say at that time, it was only static properties. We were not still able to observe or investigate what is probably most interesting. It was also the subject of all today, that is this dynamical effect like quantum friction and so on. But this, in a certain way, suggests that it is already clear that the electronic properties of a material can impact quite importantly the behavior of a liquid. Even though, again, this is a particular liquid based only on charges. So, again, water is going to be much more complicated, but at the same time is also 6 years. So we can hope that we are now a bit better and we can do it easily. So at the time we were saying, and then just go on, we were saying, okay, we move here and we enter in a regime that is completely solid, sort of a crystal. And then this was quite a bit of a discussion, especially with our friends, the theoreticians, are saying it's really unusual to consider like a solid. So is it really a solid or is it something weird that is happening? So again, the only way to reply that we had in mind was to do experiments and try to see what is the behavior. And then we basically performed the same experiment, but this time we added another oscillation, another forcing, that it was a lateral forcing, sort of a shear, and start to understand what was the response. So here we will use macroscopic probe, like in the order of a few millimeters. The system, the setup was slightly different, but the concept was always the same. And again, we measured the normal response as a function of the distance, and again, we were able to recover this, let's say, long-distance viscous behavior. And in parallel with this, we were also measuring the shear response, so basically the dissipation on when it was parallel. And when we arrived in the order of few tens of nanometer, again, we observed this transition between a liquid state characterized by basically no lateral response to a sort of, it's a more like solid-like behavior. Here the zero was really detected with the electrical contact, so we were sure to be at a real zero. And then we basically measured the response, so there was the mechanical impedance of this on the lateral oscillation as a function of the shear strain. So we changed this by changing the amplitude of the oscillation, and what we recovered with this transition with, let's say, a small shear where we observe a dominance of this conservative part, and then a crossing for larger strain until a regime where basically the dissipative part and the conservative part are the same. And this is very reminiscent of what is the behavior of simple glasses, let's say. So what we can understand is that, okay, with this, when you confine this liquid, you force a sort of organization, but it's not enough to create a crystal, but you have still something that is a solid because it responds like glass. So that was what was the response. So then we decide, okay, we really want to understand what is happening at even smaller scale. So what we have to do now, if we want to go to investigate the friction and dissipation at atomic scale, is to push further this technique and try to observe what is, if we can really detect things when you at the nanoscale, real nanoscale. So we change a little bit our configuration. So we use the same experiment, the same setup, but instead of using a liquid, we say, okay, we just increase step by step the complexity, and now we investigate what is happening to a solid object, but this time a solid object that is extremely small. So the idea was to investigate the mechanical properties of quantum point contact. So the idea was to investigate the response of a few atoms of gold confined between the tip and the substrate. So to do this experiment, the idea was again quite simple. So sorry, here was the idea was to glue a gold tip at the extremity of a quartz tuning fork, approach the tip to a substrate of gold substrate until you force the tip to crush in the substrate, and then you make a junction. The good thing of gold is that it's very soft, so you can make a good contact. And then you start to retract very gently this tip while recording the current induced by a voltage between the tip and the substrate. And what you observe when you decrease this or when you retract is that you start in the beginning where basically the current is proportional to the voltage and is decreasing gently with the surface, let's say. But then when you enter in the really last part, you observe this change of this evolution of the conductance with step-like behavior that is basically a signature of the fact that the size of the junction changes at the level of individual atoms. This is happening basically for distance, for lateral size that is below the mean free path for electrons in the gold that is in the order of 40 nanometer. So here basically you have a direct probe of the size of the contact. So here was the electrical response. And then you can also measure it by, again, in following the response of the mechanical oscillator, what is the mechanical what are the mechanical properties of this junction. And here again, we were investigating the Z primes that follows quite well this the evolution of the surface. So basically, the junction is softer and softer while you decrease the surface. And then we were also able to observe this mechanical dissipation and observe this small peak every time that you were having a change in the cross section. That is probably a signature of mechanical reorganization. But to understand a bit more, again, the experiment is allowing us, for example, to investigate the properties when you change the forcing. So the idea was there now to stay fixed on one particular configuration. Here was 11 atoms. And then start to see what is the response when you increase the oscillation amplitude. Here is in a picometer. So here what you observe is that when you increase and you arrive to this level, at the beginning you have a very small noise in the current or a very small fluctuation in the numbers of atoms in the junction. And then when you arrive at this critical value that is not that far from the size of a gold atom, you have a change in the response with much more noise and with much more fluctuation in terms of number of atoms in the junction. And in parallel, what was interesting was to, of course, studying what is the response of the mechanical response. So in this regime, a small oscillation amplitude, basically the mechanical response is only characterized by a stiffness. So it is very, very behaving like a solid, let's say. When you arrive at this critical response, you have this critical value, you observe a drop in the elastic terms and an increase in the dissipative part. And then when you increase even more, you observe that the dissipation is quite constant, while at a certain point you observe even a change and a negative elastic term. And once again, that was interesting for us is that here the response is again reminiscent of a glass. So we were before using a liquid, we make it solid and it was a glass. Now we had a solid, it's very small, much smaller than the liquid before, and we make it somehow liquid or we make it like behaving like a glass. And sorry, okay. So then from analyzing this, we are also able, for example, to have much more information. For example, what was the critical strain line that was in the order of a few %. And from this, for example, understand what are the properties of this junction and compare this, for example, to the case of a macroscopic response. So from what we measure, for example, was that the force associated to this transition was proportional to the number of atoms, and from that we can extrapolate this sigma y value and compare it exactly to obtain something like in the order of 1 gigapascal, so showing that is 1 or 2 orders of magnitude larger than the case of a macroscopic system. So indeed, it is smaller, it is a glass, but it's extremely stiff and extremely solid. And the way to understand was basically saying that this behaved like, all the deformation here is not mediated by defects because the system is perfect, but is only mediated by reorganization of the atomic plant. And then what I was saying is again that it was quite interesting for us again was what is happening at a very large amplitude when you observe a transition between let's say a positive Z prime to a negative Z prime. At that time we were thinking that it was most likely a sort of a liquid behavior of this junction, so a transition even to a liquid state. Right now we think it's more like a fact that we induce a reorganization and change in the shape in the junction but that end up like having a response that is a liquid-like. So let's say after this, with this, and after this 5 years of experience with a bit more, but especially these last 5 years of experience with the tuning fork IFM and atomic force microscopes with soft condensed matter, it was the moment to address real question like, can we investigate interfacial properties and what is happening when the liquid isn't at the interface with the atomic flat surface? And that is what is happening in the, let's say, last years. So we use again, as you see here, the same setup. Again, nothing changes in terms of the instrument, but we change again the probe. In this case, we glue a capillary. It's very similar to what Marcelo presented today with the CCM. It's basically the same configuration. Only in this case, we were not interested in the current. We were more interested to use this as a deposition tool. So the pipette here at the extremity was in the order of a few hundreds of nanometers. We approach this pipette to a flat, let's say, to a surface of graphene of different properties, and the graphene were connected to 2 gold electrodes, amenable to measure the current, not only to apply voltage, but especially to measure the current. So the experiment was like this: was okay. We were far. We approach the tip to the substrate. There is no liquid anywhere except inside the pipette, and then when you arrive to contact, you observe this big change in the frequency shift, characterized by this slow decay. That is, for us, was a signature of the formation of a liquid drop between the tip and the substrate. And then once we were there, we were able, for example, to move the drop around the samples. And we do this experiment of different sample of graphene or graphite, let's say, was with the high corrugation, again with this big wrinkle that, for example, had been shown before, but also with, let's say, a flatter surface. It's not without any defect, but it's still one order of magnitude softer. And then we displaced the drop around the surface, and we were collecting the current in the meantime. And what we observed is that every time that the drop was moving, we were able to record a current that was extremely large, and it was also quite weirdly strongly dependent on the corrugation of the substrate. So it was clear that we were observing sort of the fact that the movement of a liquid drop on the graphene was generating an electronic current in the solid. So to characterize a bit more the experiment, or what we did was basically studying the dependency of this with the velocity. So that was the first thing. So we used different sample characterized by different roughness, and what we observe is that in all the cases we observe this current density as a function that is linear with the fluid velocity. Here is just the peak. And then what we observed was also clearly that it was this strong dependency with the corrugation. So we compared different samples characterized by this sort of a density of wrinkle on the surface, and what we observed that there was also a strong correlation between the current that was generated and the surface roughness. So that was the old experiment that we started observing. It was the moment to try to understand what was the origin. So at the beginning, what we were thinking is that, okay, we are using, and I forgot to mention that we are using basically an ionic liquids. It's again charged liquids. So the first hypothesis is that it's just charging my image charges on the surface that are moving because you're moving the ionic liquids. So the good sample experiment was to use now a neutral liquid like a silicon oil, and we observed exactly the same thing. And also, if you just consider what is this sort of a Coulomb drag, so basically the movement of these charges, and you compare to the experiment, you observe that there is a very big disagreement between what you expect and what we measure. We measure always larger measurement. So to understand what was happening here, no surprise, we come back to Nikita and Baptiste. So we ask him again to help us to understand. And what end up like this was that it is indeed not, this phenomenon was not exactly a direct electron drop of the electrons on the solid induced by this image charges, but more the fact that the movement of the liquid drop generates a phonon propagation in the solid, and only because of this phonon-electron coupling you can create this kind of current. they were very kind to push a bit further the model and to provide us some data some experiments that we can compare with their theory. In particular, for example, to investigate how the conductivity or how this current generation can be modified by a bias on the voltage. So basically by changing the bond structure, the occupation of the bond structure. And that here is the comparison between the experimental point and the theory. There are still some things that we do not understand, even quite a bit that we do not understand, but still again, this proves and shows quite clearly again the fact that liquids, molecule in the liquids and electron in the solid can interact. This interact can be quite strong. The idea is to do the contrary, for example, so try to move liquids with the electrons and try to see if you can measure a sort of a dissipation. But this is going to be for the next step, let's say. And then I think that I can just conclude here. So basically, say this is what we have done here in the team. The team now is not very big, but we are quite long data we're working together. We have now a collaboration, and we have the luck to work with the very good students and postdocs that work a lot in the lab while we are doing the hard stuff. And thank you very much.